Welcome back to Network Forensic Fundamentals. My name is Phil Hagen. This is episode number 5. We're going to be talking on a different core tool than we did previously. We're going to be talking this time on Wireshark. Wireshark's a tool that I realize a lot of people have used at least a little bit, and I tend to find that most of us who have used it haven't really gotten deep into its capabilities. So we're going to take just a very brief look at what I consider to be some of the more network forensic focused capabilities of the Wireshark toolset. And I also want to start with a bit of a disclaimer. This is not going to be an exhaustive coverage of every single capability that Wireshark provides. There's actually other training that the Wireshark developers and their support that they will support and provide. So I don't want to try to overshadow the fantastic work that they've put into that training. This is really just a very brief primer to help you get off the ground when it comes to a network forensic workflow. Wireshark is an absolutely invaluable tool, but I always like to say it's a tool of last resort. And it's because in most network forensic work, we're not using PCAP files for our casework. They're still very important. We've had several episodes here in the series talking about them already. So I don't want to diminish the importance of PCAP files, but they're usually the last stage of the investigation, or at least the investigative workflow. And that's because there's a lot of the data, and going through millions or billions of packets, it's a very labor-intensive process. We want to reduce that down as much as we can and use tools like Wireshark only on the smallest amount of data that we can possibly address. We want to minimize first, then go dig deep with Wireshark. Wireshark's a graphical tool that is designed for protocol decoding. The current versions of Wireshark have decoders for over 2,500 different protocols. And from those protocols, they can extract out more than 250,000 different fields. And that's a lot of information in a ton of protocols that we've probably never even encountered before. Because the protocol use across the entire spectrum of what you might see in a case can vary, it's sometimes real handy to have a tool like Wireshark that has a lot of those protocol decoders available, so you don't have to learn every single new protocol from the ground up. Now, if you do discover a new protocol, you have the option of creating your own protocol parsers. And this isn't something that we're going to do every single time, but if you find that there's a protocol that's important enough to your case, there's going to come a point where the value of having an on-the-shelf decoder might increase to justify the level of effort required to create the protocol decoder. But again, the option is certainly yours. Now, Wireshark brings a couple of important characteristics with it. It is free, it is open source, it is cross-platform. Just the same 3 things I talked about were wonderful about TCP dump in the last episode. In this one, we're going to say the same things about Wireshark because they're all very true as well. And Wireshark also comes along with T-Shark. And T-Shark is a command line tool that is essentially a different front end into the same back-end libraries that Wireshark uses. So with very few exceptions, T-Shark can do pretty much everything Wireshark can do. Now, we've got a future episode coming up that's going to cover T-Shark in particular, so I don't want to get too far ahead of it, but I do like to, at least up front, explain that these are essentially one and the same tool. They're just different front ends into the same back-end capabilities. One of the reasons that I do find Wireshark to be a tool of last resort is because it is not suited to address large packet capture files. The general guidance that the Wireshark developers provide is however big your PCAP file is you're going to read in, you should expect to have at least 10 times the RAM available on the system where you're running it. Now, in modern day and age, 64, 96 gigs of RAM might not be unheard of, but even still, you're looking at 6 to 9 gigs worth of data before you start to really feel the pain of using an exhaustive tool like Wireshark in a RAM-constricted environment. My general rule is just for my own sake of expediency and comfort, I generally don't like to use Wireshark on PCAP files that exceed maybe 5, maybe 600 megs in size. I mean, the RAM on my system could accommodate it, but it does still get a little bit sluggish, so 500 to 600 megs is my general preference. I'll go beyond that if I really have to, but I try not to. And it is designed for this, the tool is designed for packet by packet view. And I would say this is a plus and this is a minus. it's great because you can get deep into every single field in every single packet. It's frustrating because that can be an incredibly deep rabbit hole to chase down. You don't necessarily want to look at a million packets worth of data with a billion fields in them. Sometimes you want to look at something that's a higher level. So Wireshark is definitely a tool that is best suited for those low level investigations or for protocol exploration, for research into new protocols, for example, anomalies in a given subset of data. Those are all great uses for Wireshark, but Wireshark's definitely not going to be your tool where you get your first look at case data and you try to load it all to Wireshark. We got a lot of other processes that we like to use before we get to that point. And in fact, that's a lot of what we cover in Forensics 572 is the different tools that we can use and why we use those tools before we get to the packet capture. But for the purposes of what we're going to cover here, Wireshark's still an incredibly capable tool. It's invaluable to us in our forensic workflow because it helps us to explore those protocols that might not be so familiar to you and I as human beings. The protocol dissector does a lot of the heavy lifting for us. Now, before I go over to show you a demo in my virtual machine here, the Wireshark interface can be customized. It can be configured. We're going to talk a little bit about that coming up in the next episode. But I really want to just talk through the default interface and how it's designed for you as the user, the analyst, and kind of talk about the different ways that it can be used. So I'm going to jump over real quick into my virtual machine. This is actually a variation of the SANS Sift workstation, which you can download for free on your own. It's got Wireshark and thousands of other forensically focused tools baked right in, not just network forensic tools. And the Sift workstation virtual machine is built on Ubuntu, and it is a platform that is used for a wide variety of our digital forensics and incident response or DFIR courses at SANS. We all customize them to our own needs and give you a platform where you can run with your labs. You can also work through casework as well. So that's what I'm going to be using to demonstrate the Wireshark interface for you. So I've loaded up Wireshark in the SANS Sift workstation, and I've loaded up a PCAP file already. It's called Nitroba. This is actually a standard PCAP file that's used for a lot of baselining of intrusion detection system testing. It's a public data set, so you can actually go out and download that on your own to explore if you'd like to do so. It's pretty large. It's got a lot of information in there, and it's one that we use for a lot of different tool validation and testing processes. And I'm going to go through this Wireshark interface to kind of give you a feel for what these different components are in its default configuration and how they can benefit us as network forensicators. Up at the very top here, we have a section for entering a display filter. Now we're going to talk a lot more about display filters coming up in a future episode, but this is basically a filtering syntax that is very versatile, that allows you to go in and specify a search filter that will limit the packets that match conditions based on any of those 250,000 or more different fields that Wireshark is aware of. Now, in general, you're going to get familiar with a handful of those that you use most often, or you consult the documentation to figure out which ones are most relevant or interesting to you. We are also going to cover some of the use cases for how to discover those fields in a future episode. So if that's something you're not familiar with, make sure that you keep sticking along with the series and check out what we're going to show you in just a little while, a couple episodes ahead now. But that display filter is going to be something we spend some time on more a little bit later. The next section is the packet listing section. Now, this packet listing section, I like to think of it as a spreadsheet, because this spreadsheet is going to be one row per packet that matches whatever display filter you have if it's there, or if it's absent like we have in this example, all of the packets in the PCAP file. So one row per packet, and then we have multiple different columns. Those columns are going to be selectable fields from each of the packets. Now I've left this Wireshark in its default configuration. You can see we have information including what's called a frame number to begin with. We've got a timestamp, and that timestamp is going to be based on the PCAP file. Remember back in a previous episode, we talked about the timestamp headers. That's pulled, this value is pulled from those headers. We have a source and a destination IP address. We have a protocol that's been listed. Now, this protocol that's listed here is based on what Wireshark has observed within this individual packet. So we can see sometimes it's HTTP, sometimes it's DNS, sometimes it's not actually containing any layer 7 protocol, it's just TCP. Things like the bare TCP SYN or an ACK packet, those don't actually contain HTTP payloads, so they're not going to show as HTTP. There's a length value that's going to indicate the size of the byte count that's in the packet. And then we have an info column. And the information here is based on whatever the person or the team that wrote that protocol parser wanted to put in the info field. Sometimes you'll see that it's pretty basic, especially here with the TCP SYNs and ACKs. But when we have actual layer 7 payloads, like our HTTP or DNS here, you'll see that we do reflect there being some relevant information, some context. We see that there's a query for www.google.com. We see that there's a GET request for this mail URI that's shown here. And that's because the team that wrote the dissector said, hey, this is what we want to put in these individual packets. But that's just the summary. Another cool thing in the summary, though, is that it is color-coded. You can customize these colors, by the way. You're welcome to do that if you'd like to check it out. But over on the right-hand side, you'll see next to our scroll bar, we have a visual list, if you will, or a stack of where those different protocols are observed. So we can see that down towards the bottom here, there's a whole lot of this kind of odd-looking green color. If we scroll all the way down there, we'll see that's because there's a whole lot of TCP content there. That TCP content is going to be reflected as green. The UDP content is that light blue that you saw previously. You can customize this again, like I said, or the defaults are going to still give you a pretty good idea of what's in that packet capture file, what you're scrolling in. The next panel here, which is called the packet details panel, this is actually where I spend the overwhelming majority of my time when I am using Wireshark. And this is because it unrolls every single field, every single value that's in that particular packet. So let me scroll back up to the top. I'm going to go ahead and I'm going to pick a DNS query for google.com. And if we look here, there's layers on layers in this packet details panel that give us an idea of what's present here. Now, I'm also going to give you one of my pro tips. I generally don't use the mouse when I'm navigating here in the packet details section. I actually use the keyboard because if you look over here on the very far left, you'll see we've got that arrow, that triangle. That means we can unroll that layer. And we can unroll it by either clicking on it, which works just fine, or you can just click the right arrow. And in clicking on the right arrow, I've now unrolled this pseudo layer that says, okay, we're looking at frame number 9. Now, all of this information here, it's not actually a part of the packet payload. This first section that I called a pseudo layer is metadata. You're going to see information about the timing, about the byte count. You're going to see information about, what the protocols there are that have been parsed out. This is basically just Wireshark giving us some context. Some of it is directly observed out of the PCAP file, things like timestamps there. Some of this is going to be calculated, like what protocols, what dissectors worked. But each of these can be used in display filters. Before we get too far into display filters, let's look at some of the other layers that are present here. Following the theme of using the arrow keys to navigate, even though, for example, right here, I'm walking down the list, I can hit the left arrow, I'm going to go to the parent layer, or in this case, the pseudo layer, and if I click the left arrow or tap the left arrow key once more, it's going to roll that back up. Then I can go down to the next one where we see Ethernet 2. This is, in fact, the Ethernet header. We do see in this case there are 14 bytes because we're looking at an 802.3 standard Ethernet, and we'll see the fields that are present here include exactly what we would expect. The protocol dictates the first field is a 6-byte destination MAC address. The second field is a 6-byte source MAC address, and then we have the type. And the type that's showing up here is 0800, which means the layer 3 protocol here is IP. Now, the other information on here is going to be pulled from elsewhere in the packet, just has to do with how the dissector is written. But this is going to be the Ethernet header. In the actual payload itself, we're looking at those 14 bytes at the top there. That is a true layer 2 view. Roll that back up, move down to layer 3. As we saw previously in this example, we're looking at IP traffic. That's because it's 0800. If we get a little bit further into the IP header, we'll see that the first value that pops up is the IP version. This is, of course, IPv4, which we could tell from the IP addresses in the header itself. But when we get into the IP header, we need to know what version it is. This is going to be designated by this field present here. How long is the header? In this case, the IP header is 20 bytes long, fairly standard. Walking down each of these, you'll see that it's showing me each of the fields, the IP addresses. It's showing me the checksums, the lengths. And I'm going to get a little bit ahead of the game here, because if you look down at the very bottom in the packet bytes panel down here, you'll see that this is going to include or highlight whatever I'm looking at up above in the packet details panel. So as I walk through these headers, we're going to see the same values highlighted down below. And I think that's actually super helpful, because sometimes these are very intuitive, sometimes they are not. Now let's roll up the IP header. Let's move a little bit further down. In this case, we're looking at UDP traffic. Our layer 4 content, therefore, is UDP. And we'll see that we have, we've got a source port, destination port. We've got a length of the actual content here. And as we walk continuously down the line, we'll see that those bytes continue to be highlighted. One other thing to be aware of, anytime in Wireshark you see one of these layers, or these fields rather, that have square brackets around them, it means that that's a calculated field, not something that was directly observed. So that's a good visual indicator that Wireshark is telling you that the stream index is 0. That's going to come in hand when we talk about following TCP or UDP streams later on. Once we get past the UDP header, now we're actually into the payload. And the payload itself is going to be, in this case, DNS, because we see that it's parsed out by Wireshark as that. But if we get to know the DNS protocol, we can see those fields and those protocol artifacts stand out pretty clearly. Getting all the way into the flags, we can see that this is a bitmask field. Walking further down the line, I can unroll the query itself. I see that the query was for www.google.com. I see that it's an A record query, which means I have a host name, I want an IP address. It's an IPv4 address query. And we see that it has a class called IN. But if you look in the actual payload itself, it's just 2 bytes, 0001. If you wanted to know that this meant IN class, which stands for internet class, you would need to go to the RFCs. Those RFCs are not always the easiest thing to read through. They're incredibly important documents, but they're not the biggest page turners. But in here with Wireshark, because the team that wrote the protocol dissector did that dirty work for us, we can go ahead and say, okay, that's an internet class query, because Wireshark has parsed that out. So it's a real handy way for us to ride on the shoulders of those who have done a lot of the heavy lifting and putting those protocol parsers together. So we certainly would take advantage of that wherever we can. But that just gives you a very brief idea of some of the main sections here in the interface. Now, there's one other section of the interface I do want to briefly point out, but we're going to cover it more extensively in a future episode, and that's way down at the bottom. This status bar down at the bottom is really handy, because you can see here, let's go ahead and do the query name. You see down at the bottom, Wireshark's now telling me, here's what you have highlighted. You've highlighted something called query name, and I call this dns.qry.name. We can see that right in the parentheses, and I can see this particular field is 16 bytes long. So I know the field name, which will go into the display filter, and then that field name is something that I get in human readable form. I see that it's actually just called query name. So it's a real handy way for me to get an idea of how Wireshark identifies the field that I have highlighted. Also, in that status bar a little further to the right, it'll tell you how many packets are in the entire PCAP file. And as we're going to see later on, if you apply a display filter, it'll tell you how many you have limited your view to. So what is your current scope? It'll tell you that in terms of packet count as well as percentage. Super, super handy way for you to use the interface. I'm also going to tell you how to customize the interface a little bit later on. That's going to be in the next episode. So if this view right here doesn't look intuitive, or maybe you want to know, can I change it? The answer is absolutely yes, but tune into the next episode and we'll make sure that we get you that information. In the meantime, let's talk about a couple of other Wireshark filters that you might be able to take advantage of. Namely, following a TCP stream. Now, there are some other followed streams that you can look at, and I will talk to those in just a moment. But following a TCP stream is probably the first thing most people do when they use Wireshark. And it's because it's real convenient, really handy. It'll basically take any packet that you're looking at reassemble the entire TCP session, take care of all the TCP overhead, and then it will give you this nice, concise, cleanly packaged payload of that content. And let's take a look at exactly how to do that. I'm going to go back into the Nitroba PCAP file, and I'm going to look specifically at this GET request in frame number 3. Now, in order to get into the TCP stream functionality, we right-click that packet and we get a context menu. The context menu then gives us this follow option. And if we follow the TCP stream, you'll see that Wireshark is going to reassemble all of those packets together. Now, if you look at this example, there's only one packet in each direction. However, these span, as we can see on the interface back below, a number of packets, and Wireshark has simply given us the reassembled payloads, so it's very convenient. It's also kind of cool because once you follow that stream, you'll see that your display filter has changed. It's actually limited to your view. That's why we only see that smaller number of packets in the background there. But let's just take a look at the followed TCP stream window. We can see here the GET request. We can see the response that came back from the server. It's plain text, so we're able to see that in the colorized view that you see here, with red being the client to server side and then blue being the server's response that comes back. This is a very, very handy way for you to examine just the payload portion. Now, this happened to come across in 2 data packets. If this came across in 1,000 data packets, it would look exactly the same. This is a super convenient way for you to just focus on the layer 7 payload without having to worry about the layer 4 fragmentation, packets coming in out of order, check some mismatches, all the great stuff TCP does. We just kind of put into the background and say, give me the data, give me the payload, contiguously reassembled as we see here. And there's a couple of other neat features that you've got in this dialog as well. In this case, I'm looking at the entire conversation. If I wanted to limit my view to just one side or the other, I can do exactly that. Now, I'm looking at HTTP in this case, so ASCII makes sense because it's HTTP 1.1. But if I wanted to look at that in a different view, maybe I wanted to look at that in a hex dump view for some reason, I can see the reassembled contiguous payload in that hex dump format that you're probably familiar with. Or another important one, I can do raw. Now, this isn't designed for humans, really. What it's basically done is it's taken that TCP payload, reassembled it, and rendered this in hex-based notation and put it all into one long string. This is how it appears for you and I in the interface. If we then come down and hit Save As, I have the opportunity to save this as a file, and it will actually be that entire payload. So just to give you an example of how that works, I'm going to put this in my temp directory, and it's going to be HTTP response .text because we know that it's ASCII content. I'll go ahead and save that down. And now when I bring up a command line and I go to the temp directory, I can take a look at that HTTP payload, and here's the entire content. So it's showing me that. Now, in this case, this isn't really that great a party trick. It's HTTP. It's exactly what we saw a minute ago in the followed TCP stream window. But if this were binary content, what we've just done is reassembled the binary payload and put that out into a file. This is especially helpful when you get into more advanced topics like protocol reverse engineering or doing signature generation based on indicators of compromise. Great ways for us to leverage the raw payload of suspicious or malicious traffic, even if it's just raw TCP content with a proprietary undocumented protocol. Wireshark gives us the ability to address the protocol instead of all of its overhead. So that's the followed TCP stream. Now let me close this out real fast. I want to show you one other thing that's present in here. You probably noticed that in the follow dialog, we had a couple of other options. We have the option of potentially looking at a UDP stream. And even though there's no real such thing as a UDP session, that's going to be the reassembled UDP payload. There's some other protocols in here, TLS, HTTP, even HTTP2 can be reassembled into its individual objects. And the big difference between simply TCP reassembly and let's say HTTP reassembly is that we'll see Wireshark will do things like decompress the content or de-chunk the HTTP if we see a transfer encoding chunked session. Lots and lots of other stuff that we get into in a lot greater detail within Forensics 572 about the variations of some of these protocols and of course why it matters. But that set of other options of how to decode ends up being a very convenient way for you to explore what matters most, meaning you don't have to worry so much about the overhead when it comes to things like TCP. And as I mentioned before, Wireshark does a billion things, and we're not going to cover every single one of those here. I just want to tie a couple of last things onto this just to give you an idea of some of the features that are most important, or maybe that we should avoid when it comes to a forensic workflow. Wireshark has the ability to override its protocol decoders. So as we saw in the little example, Wireshark does a reasonably good job of decoding HTTP and DNS and those other 2,500 protocols, but it doesn't always do a perfect job of identifying which protocol it's examining. For example, if you have, let's say, DNS traffic on an alternate port, it may or may not decode that, which means you, the human analyst, might look at this and say, I know what this is. This is DNS. Wireshark didn't decode it as such. I know better. And you can right-click any packet just like we looked at a followed TCP stream, and you can go ahead and select an alternate protocol. You select decode as, and then you can choose any of those 2,500 protocols to override the automated decision Wireshark's already made. Real fantastic way for you to apply the human knowledge on top of that protocol, or on top of that interface. And we also can do traffic capture. And this is where I have to take what might be somewhat of an unpopular opinion. I do not use Wireshark for traffic capture, period. And there's a couple of reasons for this. First of all, Wireshark's a protocol decoder. It's doing a lot of work. We talked about 2,500 protocols and 250,000 different fields. There's a lot more that's going on that doesn't involve high fidelity, preferably perfect full packet capture. So I usually prefer to minimize what my traffic capture platform is doing because I want to get the highest fidelity, most complete capture possible. So for me, using Wireshark just adds a whole lot of unnecessary overhead that I'd like to avoid. So I don't do that. There's some security reasons for it as well. The developers have done a great job of separating out the actual capture itself, which might require promiscuous mode, and the analysis portion, which may not. But there still is somewhat of an uncertainty of, okay, what am I really handing off to 2,500 different protocol decoders? And those can sometimes introduce security risks. I'm not a super concerned about those in most cases, but if you're dealing with true malicious traffic with high-level, state-level adversaries, you probably want to be pretty careful about using the lowest level functionality tool for the job. Not to mention the fact that TCP dump is extremely fast. It allows me to apply those BPFs as well, and I can create those PCAP files almost at whatever speed my storage and my network interface can support. So it is, in my opinion, a better tool for capture. But I'll also say, hey, Wireshark can do the function, can do traffic capture, and in some cases, like in a lab or research or experimentation contexts, might end up being a pretty good tool for it as well. But we want to be careful about using the right tool for the job. And then lastly, for a lot more information about what Wireshark can do, I strongly encourage you to check out Wireshark University. We'll put links to that in the show notes down below the video here. That is going to be your best source of information on Wireshark training because it's written by the people that wrote Wireshark. So they probably know best. This module was really just designed as scratching the surface and getting you up to speed quickly on some of the more relevant functions and network forensic focused functions that Wireshark can provide. Hope that you found this to be useful. Hope you found it to be interesting. We're going to continue to build on this in the next sessions, in the next episodes, where we're going to talk about customizing Wireshark. We're going to talk about T-Shark. We got a couple of other fun things coming down the line for you as well. Again, my name is Phil Hagen, and this is Network Forensic Fundamentals. I hope you enjoyed this episode and look forward to having you back soon. Thanks very much.